All right, everyone. It looks like it's just shortly after 1 o'clock here. Welcome back. Hope everybody's enjoyed the first half of the conference here on day one. I know I've enjoyed the sessions that I was able to sit in on. Wanted to go ahead and introduce myself. We're here to talk about beyond fault detection. So my name is Jeremy Richmond. I'm the Vice President of Sales for DB Engineering. We are an engineering and technology consultant focused on designing and operating smart buildings for our clients with data at scale and square footage at scale. And so with me today, we have 4 panelists, very esteemed in their own right. I'll go through and kind of give everybody an introduction, and then I'll let them talk a little bit about their practices. So first we have Dr. Joe Zhu, excuse me. He is the Director of Research and Innovation at Slipstream with more than 25 years of experience in commercial building energy efficiency with focuses on building controls, smart buildings, grid interactive efficient buildings, and as an engineer, researcher, and a project program facility manager. Joe is a member of ASHRAE and actively involved in the local chapter, as well as multiple technical committees, specifically 1.4, the control theory and applications, and 7.5, the smart building systems. He is a voting member of the ASHRAE Guideline Project Committee 36 on high performance sequence of operations for HVAC systems. Dr. Zhou holds a BS and a MS and a master's, bachelor's and master's in electrical engineering and a PhD in mechanical engineering from Iowa State University. His past experiences also include working as an applications engineer at Johnson Controls and a researcher and energy efficiency program manager at Iowa Energy Center. We also have Dr. Jessica Granderson, who is a staff scientist and interim director of the Building Technology and Urban Systems Division at the Lawrence Berkeley National Laboratories. She is a member of the Whole Building Systems Department. Dr. Granderson holds a PhD in mechanical engineering from UC Berkeley and an AB in mechanical engineering from Harvard University. Her research focuses on energy management information systems, fault diagnostics and control, and advanced measurement and verification. She is the recipient of the 2015 Clean Energy Education and Empowerment Award for leadership in research and the 2020 Federal Laboratory Consortium Award for excellence in technology transfer. And she was a 2020 woman at the lab honoree as well. From 21 to 22, Dr. Granderson served as the director for building technology at the White House Council on Environmental Quality. We have Troy Harvey, who is the CEO and co-founder of Passive Logic, the creator of the first platform for generalized autonomy. As the architect of the quantum digital twin standard and deep physics AI engine, his empathic systems-oriented approach to technology development is transforming the way we control systems and equipment. Troy is determined to solve the most pressing climate challenges we face by optimizing buildings, cities, and other controlled systems through autonomous control. And we have as well with us Dr. Narges Basabadi, who is an assistant professor in the Department of Architecture at the University of Washington. Dr. Basabadi also leads the Sustainable Intelligence Lab. Her research centers on sustainability and computation in the built environment. Much of her work focuses on advancing design research efforts through developing data-driven methods, workflows, and tools that leverage the advances in digital technologies to enable augmented intelligence and platform-based and human-centric design. With an emphasis on multi-scale exploration, her research investigates urban building energy flows, human systems, and environmental and health impacts across scales. And those scales are across the buildings, from the buildings to the neighborhoods, and the neighborhoods to the cities. So I hope everybody gets a lot out of this session. We're going to talk about the foundations of fault detection, the limitations of fault detection, and where we take this from here. Dr. Joe, I'll turn it over to you.
Okay, great. Thank you. So I'm going to start off with setting up the stage for today's session, which is moving beyond fault detection and diagnostics. But I'm going to briefly touch on the current state of fault detection, ASHRAE Guideline 36, related to fault detection and diagnostics, and focusing on setting up the stage for this session, which is what's beyond a fault detection and diagnostics. Again, my name is Xiaohui Zhou. I'm the Director of Research and Innovation at the Slipstream mission-driven nonprofit located in Madison, Wisconsin. So most of our today's audience probably familiar with this chart, which is from Lawrence Berkeley Lab, Jessica Granderson's group, and they came up with a report. This is graphically categorize what FDD is, which is a part of the energy management information system or a subset of the energy management information system. It's mostly, we're talking about FDD today. It's focusing on the HVAC system faults. So this is the current, there are many vendors, software vendors on the market. These are probably the popular names, you know. I won't specifically say any of these, but there are many vendors already make it commercialized, can do fault detection, and some of them are even can do some diagnostics. So you can find solutions like commercialized solution on the market, which can which more and more popular because they save energy, it's more effective. Actually, Lawrence Berkeley Lab did a very comprehensive study on smart building energy campaign and on the report on the cost effectiveness and energy savings. I'm sure Jessica will talk more about that. So, but none of these are open source, meaning these are all vendors like provide their solution, but they don't expose how they did it. Their rules, maybe some they probably will put their rule-based fault detection diagnostic, but most of the solution, they have their own proprietary software. They do potentially very comprehensive or very advanced algorithm to do the fault detection diagnostics. So their existing commercialized solution capabilities include centralize, normalize, or visualize the data collected from the HVAC systems. And many of them can do fault detection of HVAC system faults. Some of them do limited diagnostics because that's more involved. You need more sensors, more information to be able to accurately pinpoint some of the fault, the reason for the faults. So, but most of them are very limited in terms of accurately diagnostic the faults for HVAC system. Some of the vendors also can optimize the operation management, and they can prioritize the faults based on the dollar value, based on the economic impact, so that the operators can work on the most important or most have impactful faults first before they work on the other thousands of faults that potentially detected by the software or system. And many of the fault detection and diagnostic software can integrate with the workflow with their backend management system or work order system. And some of them can assist in measurement verification, and some of them can assist in commissioning of the controls. So that's the capabilities, but there are many limitations of the existing FDD software as well. In terms of how they do the FDD, PNL have this 2005, the very somewhat old publication, categorize all these methods of detect faults. But the most popular used methods are rule-based algorithms, or they call it, and another method is the black box model. So you basically, based on the data you collected from the field, you using some kind of a neural network or statistics-based systems, you can generate some models and compare the model output with the actual output of the data collected, then you can potentially detect some faults. So those two are primarily widely used in the real system, in the real building. Certainly in academia, there are many other methods to detect faults. Many public papers have been published, but we'll not go into details on that. But this is the current state. Most widely used are rule-based method and also black box methods in the real commercial FDD software. So where the FDD runs, one way of the software is run in the clouds. That's most of the commercialized vendors run in the clouds nowadays. Especially for these applications for you need to do thousands of buildings scale up. You cannot do that in a limited, just a field controller. So most of the popular software runs in the cloud because there's you have no limitation in CPU power or storage. But some of them do run. So this is, we call it the overlay system, is not actually run on the actual building automation system, is on top of the overlay. Like that, we have two kinds of categories of the AFDD implementation, way of implementation. One is the edge device, which is similar to what you do the algorithm in the cloud, but is on a special computer. But it's just located on the premise on the facility itself. The other way is just embedded in the field controller. Some are manufacturers doing chiller diagnostics, some manufacturers doing the rooftop unit, outdoor air economizer, fault detection. Those are embedded in the field controller. So what's the difference between the different way of running AFDD? This table, which is embedded in the ASHRAE handbook, showing there are much more limitation what you can do if you do that at the controller level, because there's limited storage, there are limited like blocks, calculation block you can use in writing the custom AFDD or fault detection diagnostics logic. So the overlay software have much more capability because it is widely have no storage. You can use much complicated machine learning or advanced algorithm to do the FDD. So that's bringing up to another topic about the ASHRAE Guideline 36, which is I'm happen to be the current chair of that ASHRAE Guideline 36 committee, which is write this book of guideline of high performance sequence of operation for HVAC system. I bring this up because within this guideline, there's a new section of AFDD embedded as part of the guideline. So this is actually presented the other rules for fault detection and diagnostics for air handling unit. I won't go through the detail. The guideline itself is a uniform best-in-class sequence of operation for HVAC system in order to maximize efficiency, performance, and controls. And this is listed the key measures for save energy, but I won't focus on the AFDD parts only for in today's discussion. I only show one table. There are 15 rules, or they call it fault conditions in the ASHRAE Guideline 36. This is just the first condition, just give you an example. This example is the duct static pressure is too low with fan at full speed. So the equation means if you find out the average speed, average set point for static pressure lower than the set point by a certain number, the epsilon DSP means the certain like a range of small bias. If you cannot meet the set point, and at this time VFD already running 100%, there must be something wrong with the problem with the VFD or with the problem with the mechanical issue with the fan or the fan design underside, or the set point itself is too high that the demand, too much zone demand that it's always maxed out the fan speed. So it gives the possible diagnostics, but it cannot pinpoint which specific faults resulted to this phenomenon of the duct pressure is too low with the fan at full speed. So this is a more basic rule-based diagnostics embedded in ASHRAE Guideline 36. There are other 14 different equations, similar equation, and give you a table of what you see from the equation and description, and also possible diagnostics, but it cannot pinpoint the specifics. So that's a limitation of the what you can do within the field controller. Now we're moving beyond FDD for HVAC system, is adding more capabilities beyond FDD, where the next few panels will talk about how we can make the system self-recover, self-healing, or self-correcting those. Either you did detect faults or detect a bias on the sensors, can self-correcting those and make the system autonomous control, or the software can make the static pressure reset automatically done without you actually retrofit the actual system. So automated system optimization can do that. And also whether we can move beyond FDD so that the system can do automated testing and commissioning and more. So that the next several panels will talk more of the more capabilities on the HVAC system. But beyond that, the smart building is not only the HVAC system. Smart building have many other energy systems, like you have additional IoT sensors, you have additional lighting system. Each system you can have FDD for that specific energy system. And one way is you do multiple overlay system. Each have its own AFDD algorithm. The other way is you can integrate multiple energy system into one software and integrate at the data layer or the network layer, so that you can have a single application can do these multiple FDD or even advanced controls diagnostics application in the cloud. So this shows just a general smart building architecture. One of the panels will talk about they want to build a smart building operating system at the smart building system network and integration layer, so that integrate all these building system together instead of just do the AFDD for HVAC system. So I will stop here and go to the thank you everyone. Looking for more discussion on this topic. So I think next panelist will be Jessica, right?
Well, so real quick before we jump over there, Jessica, Joe, we did get a question that came in, and since it was during this session, I feel like it's kind of very specific to what you were talking about. There's a question around, can you combine rules-based approaches with other black boxes, with one being an input for the other? So using the data that's flowing in to more of a kind of a black box approach, but also applying the rules-based approach as kind of maybe a precursor or check to it.
I think so. I think some software do combine both rule-based and a more advanced black box model. So there's a combination of those, certainly in some of the commercial building softwares. I think Jessica will have more experience than me on the actual specific software. So I'll let her to answer that and bring up to her the next presentation.
So absolutely. And it's really cool to see ASHRAE coming on and start embedding AFDD as a basis into the standard that everybody is starting to now implement and put in there. It'll be very interesting to see how that evolves over time when we start looking at system interaction. We've got central plants and supporting fan coils or air handlers or other heat recovery systems even in a building that are leveraging that, and how ASHRAE kind of tackles those. Dr. Granderson, Joe was talking about bringing things together into a unified platform. So from an EMIS perspective, how is that looking? Where is that going? You've done a lot of research on the topic. Love to get some more of that from you.
Yeah, thank you. Awesome. Well, thanks so much, Joe. That was a great setup. Thank you for really the warm welcome and for including me in today's panel. I think I wanted to start with, just a little bit of context and kind of why we're even talking about, FDD and moving beyond it and the current state of it, which is, we know from our decades of research and industry experience that our controls regularly fall out of tune. That increases our greenhouse gas emissions and utility bills. It compromises occupant comfort and equipment life and really hinders our ability for successful building to grid coordination. This is not a small problem, right? Nationally, studies from the national laboratories from our colleagues at PNNL have shown that there's 29% savings to be had just from getting equipment faults resolved and getting controls working right. And this amounts to $17 billion of cost savings potentials to our businesses, 19% peak load shed potential left on the table on average in our commercial buildings. And so what I wanted to highlight today is new technology capability that's going to help us close the gap between this potential and the as operated reality of our buildings today. The schematic on the left, Joe also showed you and gave a description of FDD tools. I'll focus my remarks on those overlay systems that are pulling data from the building automation systems, sometimes IoT devices, interval meters and submeters. And so these diagnostics and detection are kind of running continuously and identifying those really common problems, scheduling or problems meeting set point in the example, even of the single rule that Joe gave. These are really surfaced and prioritized for facility staff attention through nice user interfaces and some of the complementary capabilities that Joe covered. My team at Berkeley Lab has published some of the largest studies ever, across thousands of buildings nationally that show that monitoring-based commissioning strategies that use these technologies, FDD users, are saving on average 9% from the use of these technologies with paybacks under just 2 years. And I show on the bottom right a couple of screenshots of these large-scale studies that prove out the value. This panel kind of, I appreciate that it somewhat provocatively is talking about beyond FDD. But to be clear, we're really not yet, it's not like we're over it, we're so past FDD. The business case, the best practices, the costs and benefits have been well established, and we've got a thriving ecosystem of providers on the market. So I'm going to give 2 calls to action in my remarks. The first one being for all the folks here, whether you're, a utility program administrator, an owner, or sustainability or facilities lead, or whether you're representing a market transformation entity. Real strong call to action to integrate these technologies into your efforts today. Now, FDD users are really saving quite impressively. The software automates the identification of problems, but getting them fixed is a pretty manual multi-step process. Someone's using the technology, once a problem is found, they have to submit that work order, often get back to the control system to change programming there. This can all take months for problems to get resolved. Staff get bogged down in what otherwise is pretty mundane work. And they're confronted with a tremendous number of faults. Recent work that my team has published has shown, just if we're looking at air handling units and terminal units, 245 faults every building every month to sift through. To really overcome this status quo of, it's not really a problem finding problems, it's a problem getting them fixed. To make the technology even more valuable, we've been partnering with the industry to move from detecting and diagnosing faults in an automated form into delivering fault-free optimal controls. So now, rather than that multi-step business as usual process, we're resolving problems through software in a matter of hours with what we kind of in shorthand refer to as a fix-it button. So I show in the bullets here the most common and persistent and impactful issues in our buildings that can all be corrected in software. They don't require a physical wrench turn. I want to highlight that the things we're doing here are also converging analytics and optimal control in some of the first ways ever in single product offerings. So Joe talked about the ASHRAE Guideline 36. Some of the strategies we've shown here are using the fault diagnostic systems to push those best practice reset strategies out to our air handling units without going bottom up through the building control system and reprogramming it. So all of this frees staff for the hardest problems, really lets us focus attention on maintaining in-tune operation, and importantly gives a software-based infrastructure through which we can really scale demand flexible, low carbon buildings. And I want to acknowledge our early partners in this work, all who are mentioned on this slide in the bottom portion. These solutions so far have been integrated into 7 FDD offerings, tested in the field across, integrated with several BAS types and building types and HVAC system configurations. And we keep at it. We're expanding our fold of industry partners who are integrating these software-based corrective action and optimal strategies into product. And we're also expanding into demand flexibility, demand management, and automated functional testing. And doing that with the ability to resolve the root cause of failures. Really critical capabilities. So my second call to action today is really for owners and FDD software and service providers to reach out to us to partner. We can help the owner community learn how to use and acquire these new and emerging capabilities. We provide direct assistance to providers to integrate these solutions into your offerings, really converging that optimal control, fault correction, and fault diagnostics. I welcome folks to contact me. My email is listed here, and a URL to a website where you can use more, learn more. I'll conclude with just a couple words on emphasizing really why this technology is the future. The Bipartisan Infrastructure Law and Inflation Reduction Act have driven really generational investments in building retrofits and electrification. And we know, again, back to my first slide on context, without attention, savings erode. So these smart building software technologies are critical to ensuring that the value of those investments persist as operated over the lifetime of the building. We are confronted with a retiring workforce in our industry. Simultaneously, a next generation that was kind of born on and really expects networked intelligent systems in their work life in the same way as every other aspect of our lives. And these energy management and information systems, or smart buildings software technologies, give that workforce the automation and modernity that they expect, along with really supportive automation capability. Lastly, we're seeing this tremendous industry-wide mobilization around the need for speed, climate urgency. Then at the same time, we're kind of asking more and more and more of our buildings. They've got to provide healthy indoor environments to occupants. They've got to be coordinated with a renewable supplied grid, integrate across an ecosystem of distributed energy resources, and operate with minimal net zero greenhouse gas emissions. to that end, the EMIS technologies have already done a lot of the legwork that we need to scale. So they're doing the hard work to integrate across all of these diverse system types, data models, and equipment configurations. And they're increasingly being adopted throughout the commercial sector. So we have now, to use to our advantage, this software-based infrastructure to tap into, to continue kind of using that as the pipeline to keep pushing control and analytics updates to our stock. So I'll kind of leave you with that vision for the future, and thank you for your attention, and turn it back over. Thank you to Jeremy on facilitating.
All right. Well, thank you. One of the things that you mentioned in there was a couple items. One of them around autonomous feedback back to the systems to correct inefficiencies, whether that's in programming or set points or loop tuning, etc. But you mentioned another one in there, and I'll let Troy talk to that first one here in a second, because I know he's got a lot of thoughts on that. The other one that I think is very interesting is around the functional testing.
Yeah.
Right. Being able to validate equipment. So a lot of my background comes from operations. So the only time you called the facilities desk was when something was broke. So getting from that reactive to the proactive. And when we start to think about systems and data's at scale, so it's not one building, one floor, one air handler, or a handful of VAVs. It could be 100 air handlers, it could be 100 rooftop units. And we just start to think about, those ways that we can check economizer operation. How do we make sure our economizers are working? Well, if we run a little bit of fan energy at 2 o'clock in the morning, when we know that we have a large gap in temperatures, that's a very easy way to kind of tell, are we pulling return air, or are we getting the economizer operation control? Yeah. And getting into that routine of that functional testing, and using that functional testing as kind of a preventative maintenance procedure, so to speak, to identify where you have these inefficiencies. I see there's only a handful of platforms that I've had the opportunity to look at that have that capability today, but I'm very excited for where that's going in the future.
Yeah, absolutely. And it's very indicative of what you open up when you're able to combine robust and rigorous analytics with the ability to interface with the control system. So what we found there, Jeremy, is that as soon as we can interact between the controls and the analytics at the same time, we're able to drive the system into different operational modes, kind of back to back to back. And what that gives us is the ability to then diagnose, pinpoint, isolate root causes of failures in a way that you simply can't when you're just passively watching the system across the seasons. How many times we've all been confronted with the case, and back to Joe's point about diagnostics, how many times have we gotten to the point where we're like, I don't know if it's a bad sensor or a leaky valve. I just can't discern those conditions from one another. So what the FDD combined with the integration with the system and the ability to actuate gives us together is a whole new set of capabilities. So we can take corrective action. We can start shortcutting the implementation of supervisory control. If we don't want to go BAS by BAS, not everyone will want to do that, some will. And we can move into this, commissioning with root cause identification, not just like, oh, sorry, you failed the test, but you failed the test and here's why.
Exactly.
So yeah, thank you for the comment.
No, absolutely. And I look forward to getting more into that when we get to our moderated part of the conversation. But Troy, when it comes to the autonomous functions, talk to us a little bit about your experience, what you guys have seen from going that method, as how it impacts everything from the equipment, the energy, and how that scales and can impact the sustainability of the portfolio.
Yeah, thanks for the intro. And, I think, both Joe and Jessica really sort of set up what I want to talk to people about. And I really want to have people sort of switch paradigms with me for a moment. And let's sort of imagine a different future. We have a future that we've been sort of building on top of, quite literally since the mid-1800s. All of the big automation companies were all born out of the mercury switch thermostat in their own region of the world. And we then invented PID in the 1920s, and we just sort of been piling stuff on top. And we've piled to the point that we've got all these plates spinning in the air. And here's three things about our industry that I think it's always worth stepping back on. Buildings aren't just buildings. This is the coolest robotics challenge in the world, the biggest controls problems. We have the biggest controls marketplaces, and we're about 20 to 30 years behind every other industry. So at Passive Logic, we said, what if we reinvented this? And so we're focused on designing a platform for generative autonomy for buildings. And that's built on top of a digital twin standard for autonomous systems. So imagine if you want generative autonomy, be able to describe any kind of autonomous system and be able to control it instantly, then you also need a language for describing autonomous systems. And this leads to a second question. What if our entire building lifecycle journey was an interactive workflow connected by these digital twins? That we could pick our own journey, and all of those tools, from the manufacture of products to the design of buildings to the engineering and the install and commissioning and the operation, maintenance management, and the building of tools that plug on top, could be a continuous workflow. And what if we had full autonomy? We were no longer trying to program sequences for buildings, which we already established, world's most complex systems. Not only that, they are what we call a systems of systems problem. And no matter how smart you are, and no matter how big a team you have, and no matter how many millions of dollars you have, you will not actually be able to control the state space of a building. It's not possible. So how do we make that so we can make it simple that everybody can do it, and it can be not just optimal, but actually work? So who's Passive Logic? Today, we're the largest advanced controls team in the world. We have team members from AI digital twins to building science and generative design, and the largest team working on what we call differential programming in the world. And we're backed by some of the biggest players, the biggest owners of buildings, and some big tech players. And we have R&D areas from autonomous control platform, digital twin software, digital twins themselves, new kinds of AI for this generative autonomy space, and this differential compiler workflow. So I'll give you a little bit of a taste of this. If you've ever used Energy Plus, I'm one of the first Energy Plus users that's out there outside of the DOE. And what we knew is it's going to be too slow for our application to solve some of these problems. So today we're about 7 orders of magnitude faster than Energy Plus GenOp at solving a set of problems that, we can solve a lot of problems, but that's one that's like, there's an overlapping Venn diagram. So give a little bit of flavor for the kind of work that we're doing. And that's built on this new kind of compiler tech we've been working on called differential programming. And what differential programming does is it allows compilers to compile not just your code like normal code, but it compiles the derivative of your code in the reverse code. And this is the fundamental driver behind what makes deep learning work. It's not about neural nets. Neural nets, they've been around since the 1950s. It's differential programming that allowed us to train large neural nets. And today, this open source project, we're working in the Swift language in collaboration with multiple companies, including Apple and Google, is about 200 times faster than TensorFlow and a little over 100 times faster than PyTorch. So this is how you can drive AI that both inferences and learns at the edge. Okay, so why are we all talking about? Well, buildings, as we've talked about, are the single largest sector of the energy economy. And the thing that really spurred Passive Logic to get started was a paper that was commissioned by the DOE about 18 years ago that showed that if we just controlled and commissioned the buildings we already have, no big retrofits, no new equipment, we'd save 40% of all the energy. So it's important to understand this isn't like turning gas cars into electric cars. This is like getting rid of all cars, right? So this is the single biggest opportunity. And it's just sitting there. It's cheap, right? It's like this low-hanging fruit. So what are the challenges? And we talked a bit about this, but the first is nobody here has actually seen a smart building. Smart building is a euphemism for connected. And that's a problem because buildings, as we said, they're systems of systems problems, and they're only getting more complicated. And we have no organizing intelligence in buildings. When I hired my VP of software from the tech industry, and I told him that he could have a multi-million-dollar BMS in a large skyscraper, and there's nowhere in that whole BMS that understands anything about a building. It was like mind blown, right? Like, but that's the world we live in. I want everybody to at least walk away with this. We aren't programming buildings. We are programming the world's most complex robotic systems. They happen not to move, but in terms of degrees of freedom, as we talk about in robotics, a Tesla has an order of 100 sensors. It has 3 outputs, steer, brake, and accelerate. An industrial robot has 6 axes of freedom, plus maybe 20 sensors. The largest buildings in the world are headed towards 1 million IO. It's orders of magnitude more complexity than anybody else deals with. And we're still trying to do it with like 1920s PID and 1800s set point control, all like weaved together in a supervisory controller. This is not really possible. And that's why every project's kind of a crap show from the start. So the other thing is every building's a different topology, right? So we can't just do what the car guys do. They can build one platform and they can mass produce it. But every building's a unique architecture, engineering, systems, equipment, topology, location, and so forth, right? So generic deep learning is not sufficient for this problem. And we'll get a little bit more into that. The net result, and this is what we were talking about, Jessica was hitting on this point, with decades into the BMS market, we've really only taken on about 3% of the commercial building market. It gets more abysmal when we go into industrial multifamily. And below that, it's single-digit percentage points of penetration. So it sucks at the high end, and it doesn't exist at the rest of the marketplace. So how do we solve that problem? Jessica also touched on this. Very small percentage of the people have skills. And when you go out to integrators, the mean age is in their 50s. So what are we going to do next year and the next decade as that group of people ages out of the market? And then finally, I think this is really worth noting that this is a pretty typical diagram. We see this in all of the different publications. We will essentially dive in integration effort before we actually get this done. We are just not going to piece and part a bunch of point solutions together in every building in the world. So we need more of the iPhone that we can pull out of the box and just go. And then I'll just return that deep learning problem. Why can't deep learning save us wholly? It can solve some problems, but every building's unique. No one model fits all. By definition, it's a whole year to get a data set, right? So if I want to I'm not talking about optimization, I'm talking control. If I want to control a building, I don't have enough time to sit there and watch that building to learn on it before I deploy. So we need something more. So what is an autonomous building? Let's talk through this. So single purpose autonomy, we're all familiar with this notion. You're control only, you're training once, and then you're assembly line deployment. But that's just one piece of what we need in the building market. We need a framework for generalized autonomy, one where we can autonomously assess our own environments and our values, meta-program our own unique topology, and be able to have a runtime that can learn and train all in at runtime, given the changes that are happening at the edge. So let's talk about levels of autonomy, because I think it's worth really designating how smart is smart so that we know what we're talking about when we talk about these different technologies. So level 0 autonomy, this is what we were talking about. Joe was hitting on this. Algorithmic control, this is 99.999% of the marketplace today. What you see often in the whether it's model predictive control, black box control, gray box control, we're usually talking about level 1 control. This is system tuning. You're putting a smart thing on top of a dumb thing, right? Like the BMS stays the same. And what we can say about putting smart things on top of dumb things, you don't get a smart thing. You can get a slightly less dumb thing. So I think the easiest way to think about this is you can't make full autonomy out of cruise control. You can't make fully autonomous buildings out of conventional BMS. So what would level 2 be? Sequence generation assessed. Jump into level 4, real-time sequences. This is where the dynamics in the building in real time are being interpreted and sequences are being generated for those dynamics, dealing with all of the things that are happening in that building. And level 5 is what we're really interested in. It's the systems of systems program. You have not just one vehicle like you do in autonomous vehicles, you have this whole fleet of subsystems that all have to be coordinated together in the building to really solve the interesting problems. And kind of back to that democratization problem. Unless we focus first and foremost on how we get this installed, it doesn't matter how efficient or how good anybody's control is, it's not getting into the building in the first place. So really focusing on scalability on this part above the autonomous vehicle space of level 0 through 5. How do we think about self-guided install, self-commissioning, and then eventually getting to peer-to-peer interactive buildings? So what we're talking about is today we have fragmented control. If you bring that under one hood, so you have a single world view that you can manage, aggregate, and automate all of that so that you're generating a coordinated control set of sequences to everything in unison, right? And one of the things that I think is actually interesting when you sort of start piecing deeply at our existing systems, we're often trapped in our own paradigm that we don't see all of the control that lives between the subsystems that have their own control loops. And that's often most of the problem. So how do we get this? Well, one piece is having a digital twin standard. So I think we could talk about this for an hour on its own. So I'm going to just really jump fast to what is a digital twin? And I want to just frame, because this is an active term, and I think everybody means something a little different. And what I want to make clear is it's not just putting BIM in the cloud. So we ask this question a lot here, what is a digital twin? And that typical BIM in the cloud, well, we don't feel like we need to rename things. That's just BIM. We can maybe add time series data to each of those elements. So that's BIM plus time series. That might be the foundations of a digital twin. Here, what we think of a digital twin as, and what Quantum was built for, so we can make autonomous systems, is it's visualizable like CAD, it's queryable like a time series, it's simulatable like a physics engine, it's introspectable like a semantic graph, it's callable like an API, inferenceable like a neural net. It's trainable, it's normalizable, it has this collaborative format that we can use across different applications, and then it's componentized so that we can actually sort of do this composable AI with. So that's how we think of digital twins. We think of all of these as their own unique thing, but together it is at the center of that Venn diagram of what makes a digital twin different than other things. Let me just give you two views on this, and this is, again, just focus in. In digital twins, we think in two big topic areas. One is physics simulation. This is what you guys are probably most familiar with. We would call that in this AI space, a deductive inference, right? You're deducting the future. So I'm at this time and place, and I'm going to deduct the next minute, and then the next minute, the next minute. And that's pretty neat. You can do a lot of stuff with that. You can do model predictive control, but far more powerful is what we call abductive. And abductive is when you are saying, this is what I want to happen in the future. And you can simulate backwards through time to how would I control it now? And that becomes a really foundational piece for how do you build autonomous control. Okay, so we've got autonomous buildings, we've got digital twins. Now let's put it into a usable paradigm. So let's go back to our diagram, and I'm going to focus on just these two pieces here. So an autonomous platform and a tool to build autonomous systems. So how does that workflow now look? So we've thrown out sequences, we've thrown out conventional procedural programming, we've thrown out all this sort of conventional notions, and we're now let's align it around the work we already have to do, because you're gonna draw up plans for doing a wiring diagram for how you wire it to hand to the guys in the field. Well, you're gonna have to do that, but normally you get paper. You're gonna have to design your system topology. You're going to have those diagrams of what does my system look like to give to the guys in the field. Normally you just get paper. How can we co-opt that and make a connected digital workflow that gives us free control at the end and then solves everybody's problems downstream by giving them the digital twins they need to plug in the services they want on top of buildings. So here we're drawing what our building looks like. We're importing CAD, importing scans if we have it. We drag and drop our sensors and our IoT devices. And what are we doing? We're building up a model, a thermodynamic model, a location model, an IoT, a sensor model. Then we diagram what our systems look like. Again, making this accessible to, we have to make this work for Boiler Bob and HVAC Harry if we're going to scale this industry. So this looks like Visio, but each one of these components is a fragment of a neural net that is this digital twin that is combining sort of the technology of deep learning with the technology of physics. And when they're building up this network, this diagram, they're building up a neural network that represents that system. We can generally then design the control system from that. We know where the sensors are, we know where the controllables are. We can automatically point map and take care of all of the linguistic or semantic side of, am I talking to BACnet or KNX or analog? Do I care? No, you don't really care. That's a secondary set of needs. Like we today are so buried down in the network stack, and we're about 5 layers away from where we should be working. Because the system has its digital twins, you can start to do things like automatic commissioning. So this is the other half of the problem, right? If we can't commission our buildings, it doesn't matter how well we control them, they're not going to control well. And we can continuously commission them because we can vet them against their digital analogs. And then once you have digital twins, you're generating those digital twins and you can deploy them onto a device that can consume digital twins and generate control and bring that world in the building under one umbrella, one view that's doing the sensor fusion of everything that's in the building and doing that control side. And then because again, you know what your building is, your system knows what your building is, you can automatically generate the analysis and analytics and all of the management information that we need to interact with our building. And finally, we can't really get to smart cities or smart grid unless we have smart buildings, right? Like smart buildings are really the major agents of a grid. And so if those buildings can't represent themselves in an economic forum where they're saying, hey, you know, grid, what's the futures in the next 12 hours of electricity? And by the way, I can figure out what my loads will be, and I can interactively negotiate that. We can't really solve smart grid, right? So you have to have smart agents to have smart grids, which gets you smart cities, right? So that's a walkthrough of how we think of the future of how building automation could work using an autonomous system platform and the work and the R&D efforts that are happening here at Passive Logic.
That's awesome, Troy. I think there's a lot of points when you were talking about the levels of autonomy, right? And I kind of immediately took that back to, you know, when I was doing research about, you know, autopilot on Teslas and the level of autonomies and some of the problems for adoption and you know, how much autonomy did you need in order for everything to work properly? It's very interesting where that's going in the future. And I definitely don't disagree that when we start talking about like the level 1 of you're not making a dumb thing smart, you're making a dumb thing less dumb. And when we get into just some of that automatic control, I think there's still a large gap, and I know we'll probably talk. We'll get to it here in the moderated section, just around adoption from the operations teams and how much, you know, they're used to I've got a wrench. I know how to work on that equipment. I know how to program that equipment. I know how to run that equipment. And now we're essentially talking about changing the dynamic of how all of that goes.
Yeah, I think there's two things there that you're pointing at. One is I think that a lot of the industry discussions are about standardizing the past. And I think like things like setting what are our levels of autonomy for the industry helps us provide standards for the future. And the SAA was very, forward thinking in establishing levels of autonomy so that the automotive industry could really talk about it. And we're big proponents of doing the same thing here. On the flip side of what you're talking about also, is this accessibility, that if the industry is just talking about energy efficiency and regulations, but not talking about the user experience of Boiler Bob, we've already failed. And so our philosophy here is we're going to give you an awesome user experience and you're going to get energy efficiency whether or not you care. That's not what we sell. We sell a better, faster, easier to install automation system that happens to give you the best energy efficiency.
That's awesome. So I want to pivot over to Dr. Basavati, because as we're talking about twins and we're talking about the not only the work within a building, but how building A is going to impact building B, and building B impacts building C, and next thing you know, we start to talk about impacting campuses and moving forward. I'd love to have you talk about your research in that area.
Sure. Thank you, Jeremy, for the introduction. And I'm going to share my screen. You should have my screen, right? Great. And thank you for the insightful presentations by everyone. It was great to learn more about your work. And regarding going beyond the building boundary and looking at larger city levels, so there are significant limitations, not just technologically. So at this point, currently, FDD and other smart building technologies are limited to individual buildings or campuses, which still are few. And that scarcity of the widespread smart infrastructure across the city makes us limited to making a real digital twin at the scale of the city. So today's my talk focuses on hybrid twins, scaling up digital twin from building to city levels via a hybrid approach, looking at machine learning and physics-based simulation. So as Jeremy provided some background regarding my research area, my focus is mostly on computation within the built environment, and much of my work has focused on developing frameworks, methods, and tools, and how to bring the power of AI, machine learning, automation techniques into conventional simulation models to help with design, planning, and policy making, with testing the ideas and helping with decarbonization. So the statistics are very wide public knowledge, and previous presenters discussed them and set the background very well. In this context, many cities worldwide have committed to achieve net zero carbon emissions by 2050, which necessitates significant reduction in energy consumption from buildings, which are the largest and fastest growing sources of emissions. Still, without knowing how energy is used in cities and how modification scenarios would likely reduce the energy consumption is a challenging task. At the same time, we are living in a very interesting moment. Cities are currently witnessing rapid advancement in smart building and city initiatives, the Internet of Things. AI innovations and infinite computing and multi-sensing technologies, along with big data, georeferenced big data, which have significantly influenced our abilities to understand interconnected problems within the built environments, and specifically opportunity for pursuing sustainability and decarbonization. And I believe the convergence of the digital twin technology, big data, and emerging data-driven techniques, including machine learning and physics-based, at the same time keeping physics-based urban building energy modeling for kind of accelerating this transition at a scale. What we mean by digital twin, Troy discussed very well the definition of the digital twin, which is a representation of real world object or asset or system, which dynamically fueled by real time data and intelligent functions, AI-driven analytics, enabling monitoring, modeling, and what if scenario analysis, optimizing across its life cycle to help decision making for efficiency and informing interventions. So at the larger city scale, so it's much far away focus and building, or where we have that smart infrastructure. So here with live connection, it doesn't mean every second data stream kind of decisions or connection, but still yet it's constantly kind of have a relationship between that emerging abundant data and those decision-making processes. So the evolution model of digital twin, if here I want to connect it to a larger city scale, is structured around 4 maturity levels, starting at level 0 as a basic digital model, probably what we can call it more a BIM, as Troy discussed it very well. And moving toward the level 1, one-way data flow from physical twin to the digital twin, and most recent progress as highlighted by Jessica, introducing a bi-directional relationship, allowing the digital twin not only to read data from the physical twin, but also enact as self-corrective function. And as we look ahead, the goal is to establish a closer and multifaceted connection between the digital twin and the physical twin, with a web of various aspects to be explored beyond the HVAC systems. And with a city level digital twin, it follows a hierarchical architecture encompassing sub-DTs, which are here building DTs. And we should say that the larger scale adaptation, if we are going to say about a city level, even we don't have a physics-based simulation model for a city. There are relatively few cities, or we can say that they're existing. And then arguing for an energy model for a large city scale, it's fairly in its early stages, with the kind of idea around its connection with digital twin concept. And currently FDD and self-correcting systems is limited, not technologically, but more in terms of application now to the individual building level and campuses, which are still few. And with the larger city scale, so we don't have that widespread infrastructure at the point which limits that scalability of such digital model, digital twin for a city level. So what UBM urban building energy modeling can help as a crucial tool, can generate the essential quantitative energy information and enabling that holistic optimization of energy system at multiple scales of building, neighborhood, and city, and can be either a physics-based modeling or a data-driven modeling. So the physics-based modeling relies on fundamental laws and equations from physics to predict system behavior. And at a larger scale model, even we're dealing with less accuracy, as we need to rely on archetypes that represent energy use and building stock. Data-driven models mainly identify statistical pattern in data and predict from those patterns. And as I said, each of them have their own limitations or strengths. Physics-based models have limitations around methodological uncertainty and oversimplified archetypes data. So then it's a question of how they represent the real world situation, and that they're computationally intensive and time consuming. And data-driven models, which are based on actual data, so they can be more accurate, but they rely heavily on granularity, quality, and availability of data. In a recent or ongoing work, what we are trying to bridge the gap between static UBM platforms and dynamic digital twin platform, with linking the digital twins data to data-driven and physics-based simulation. Technically, this hybrid approach aims to use the strengths of both methods, with physics-based simulation for generating synthetic data, where we don't have smart infrastructure or data possible for the planning purposes in a larger city level, and running what-if scenario analysis and addressing that scalability issue. And data-driven approaches utilizing artificial intelligence, machine learning, automation technique to overcome constraints related to data availability, as well as computational accuracy and efficiency. At the same time, we were looking at reducing the uncertainty around occupancy factors in large-scale urban energy models. We developed a framework and a tool to synchronize human social dynamics through social media interaction and identifying the load and more representative occupancy for the city based on those georeference data. So as here, we made the tool for a national level exploration of geotagged data on infrastructure and see how the energy loads and environmental issues. So here, when we are talking about energy efficiency, can be seen at the same time. And with the University of Washington, currently, we are exploring with this platform that we have developed, so still is under construction and ongoing work. We gain here access to smart meter data from buildings within the UW campus, and we're trying to analyze the time series models and extract the pattern and identify the inefficiencies and guide some prioritization for energy efficiency adjustment. And as I said, so we are looking specifically here how to reduce the uncertainty of the model based on understanding that social and human mobility across the city. And some the analytics gaining kind of insight for interventions. And I will conclude my presentation here with summarizing the advantages of a hybrid approach for a large scale at the city. So we will all discuss and advocate for the kind of adaptation of a widespread smart building infrastructure. But at this point, not all of the cities have at such large scale. And then at the planning and policy making, how a hybrid approach can help. A hybrid approach with linking the digital twins data, where we have, for example, a campus level, we have a smart infrastructure for some of our buildings, not all of them. And we are helping, getting help from data-driven and physics-based simulation to generate synthetic data in the absence of data, and increase that scalability and enhance the accuracy when we, at the larger scale, we are looking at other available data, such as dynamic human movements, mobility across the city, to have more representative occupancy profiles instead of static occupancy profiles. And with dynamic transformation here, making a shift between static models into dynamic environments powered by real-time data and intelligent functions and analytics and automation. Thank you.
Thank you. That was phenomenal. I think, you know, as especially on like the policy, so you touched on something there right at the end around integrating more occupancy based information into some of these models. It will be interesting to see how, from a policy perspective, we tackle that, just from a data privacy and constraint perspective. And, you know, bringing that in, and whether it's we're looking at it from a city level, or if a real estate owner, maybe a large REIT or somebody like that that's got, you know, tens of millions of square feet that they're managing, how they're using twins from that, or how they could use twins from that perspective to drive the sustainability efforts across that portfolio. So I'm very eager to see that. Yeah, I don't know if you have any thoughts on that. I'd love to hear them.
Sure. So regarding specifically that occupancy component, which at a larger city scale can be very helpful, because the state of the art just relies on a static profile and reduced ordered model. So here the purpose is that, so how we can make the models more accurate, reduce that uncertainty, kind of bridge that gap for larger scale. And still, the result of our work shows that how the profile of energy consumption in New York City, in Chicago, in Seattle, and the occupancy profiles that we are extracted from geotagged data from mobility, social media, they're kind of the match. So with 95% kind of accuracy. So it shows that can be a good representative. And even with the large scale campuses, such as, for example, UW's campus, still can be insightful. But then with the scale of a building, how it can help us with that data granularity, I think it can be just, it's not comparison with when we have that smart infrastructure in a building setting and collecting occupancy information, but still it can be very insightful. And some recent work, in addition to social media data, they're looking on GPS, mobile information, that we see that it's kind of it's going to be used more and more, so it can be more insightful. And I would say that for larger applications, it can reduce uncertainty significantly, but at the building scale level, so probably it's hard to say that. It
Sure.
can be.
Sure, we got to do a little more investigation down that road, I think, to see how that pans out long term. I know we've got looks like about 15 minutes left of our panel here. I just want to remind everybody you should have a Q&A button on your screen if you have any questions for the audience. I know we've had a couple come in so far. Feel free to drop your questions in there. But I'd like to kind of maybe take this all the way back to the beginning. So we've gone, I think, full technology spectrum here from fault detection, basic fault detection, all the way through twin interoperability to establish to look at city level utilization. And so you know, I'm a big proponent of saying, hey, there's a lot of fault detection systems out there, but not a lot of fault detection and diagnostic systems that are out there. Joe, what can you talk about? Like, what do you see? And I'd love to get everybody's thoughts in here. The technology has been around in buildings for over a decade. It's had various stages of adoption. What do you see as kind of the resisting factor towards fault detection systems going through? And I'd love to get everybody's opinion here.
I can start. So to actually diagnose the root cause of those faults, need more information. You need more sensors to collect data, and you need more advanced algorithm to like match the patterns for certain faults, like root caused by certain problems. So once the proprietary or more advanced algorithm development effort, more cost to implement, to install and implement sensors, which I know everybody knows here, building industry is kind of cheap industry, so we don't have like a high budget for building operators to pay for expensive system, even though it could potentially diagnose root cause will help the building owner. So I think cost is one thing, and effort and more needed for install more sensors and collect more information and more advanced algorithm development by certain software company potentially prevented to wide adoption, or because it's more difficult to find the root cause, you need more information, more advanced algorithms. So that's my first take.
Okay. Jessica, what are you seeing from on the research side from those inhibitors to adoption there?
You know, I have like, you know, five thoughts rushing front of mind simultaneously. I do want to say that, you know, in spite of some of the challenges around diagnosing certain faults, we do see, I'm going to go back to, we do see that users of FDD are saving a 9% on average with a less than 2-year payback. So clearly there is deep value there. Mm-hmm. I think one of the issues is it still takes time and commitment from a person to champion these solutions internally within their organization, get buy-in, specify them, procure them, lead the change management to see them through into standard operating procedures. I think, you know, my team in the DOE have definitely assisted with some of those barriers, providing, you know, resources, spec templates, best practice guides. And I think while there is still that great benefit to be had, you know, there's still highly committed teams to see one's way through to that benefit. So these, you know, fundamentally process-based technologies, not efficient widgets, right? And that's really at the core of it. You know, it's not a high efficiency rooftop unit. You can't just install it. Right. That's one thing. I mean, I think we talked about the diagnostics. I do see still that there's huge value being gained, even with our challenges there. Fundamentally, the main point I would like to draw out is that I think we're at an exciting place of kind of embracing and recognizing a paradigm shift. That's really where, you know, it used to be, we're thinking of all the rules we can get together, all of the algorithms we can run to find every single problem. And a lot of times that's symptoms. where we need to go and where I think we are shifting is more of a like 90-10 kind of eyes on the prize approach, right? The top, I don't know how many, 10, 20 most impactful problems that we see time and time again. A high certainty diagnosis of those problems, and then software-based correction wherever possible, integration with work order systems to get the fix made when it's physical in nature. And I think if we really drive towards that vision, we're going to see a lot more value out of the back end with a lot less upfront investment, and then have that foundation to layer more and more upon to really start peeling back on that remaining 10%. And I think that's the big paradigm shift to kind of get unstuck from some of today's status quo.
Yeah, I know. I was listening to an earlier panel, and Reed Powell and I think Pete Segal, both from McDonald Miller and ATS Automation, respectively, both came out and said, look, we thought this was going to be great. We're going to have some fault detection software. We put it out there. We find out that, well, that didn't really work. And we needed to provide the building owners kind of an on-ramp. Yes. So that they could get up to speed with the new technology that was in their buildings and how that was being leveraged and used. As well as, I definitely agree with the work order integration component, because that's how, like, just knowing you have a problem is great. We know we have a problem. How are we going to get it fixed? And so having that easy button that allows you to send that ticket to your maintenance team internally to have them go out and look at and resolve, or, you know, if it's an issue that's significant enough to send that out to a maintenance provider to come in and repair that issue. I think those are kind of key into getting that value and seeing that value come through. Troy, there was a question that came in here around ROI and how do we make that ROI more obvious to buyers and stakeholders, and being on kind of that product side as it relates to this kind of a problem, right? We know that at some level there's low adoption on systems, even though there's plenty of documented use cases of value. What advice, what have you seen? What could you say around that?
Well, you know, I kind of touched on this earlier, that I think business models have to change. You know, some of the principles that we think of here, it winds back to a book I read by Amory Levins when I was 16 years old, that basically said, if you want to sell energy efficiency, don't sell energy efficiency, right? And so as long as you're talking in ROIs, you've lost 95% of the audience. I mean, most people can't do the mental math. If they can't do the mental math, they don't have the capital to do it. And so what I think we as an industry need to start embracing is like, what can we solve now? And so here we, you know, have a philosophy that, you know, our product should be competitive with your alternates right out of the gate. And we're going to give you energy efficiency whether or not you care. And I think that starts solving the problem. And it's within this this fault detection conversation, I think it fits this other piece that I think one of the biggest barriers is integration. When you talk to the people in the field, if you take one complicated thing, a BMS, and another complicated thing, a fault detection system, and you strap them together, you didn't get a simpler thing, you got a more complicated thing. And so that's for the installer who's being tasked to do this, that's rarely in their interests, right? You're putting more work on them for which they may not really receive more value on their end of the business, and yet they're making much of the business decisions, right? So I think that's something as an industry we need to start embracing more of.
All right. And Narges, there's another question in here, maybe for you, and then maybe even for Joe, but the question came through about how many sensors do you need for a building to be a smart building? What would your answer to that be? Where would you go from that stance?
I think it's a hard question to say Probably Joe can help better with this question. So ideally, in an ideal situation, if we could monitor many aspects, so it was better, but I don't have an answer with how many. Joe,
Yeah, I apologize. Kind of a trick question, so to speak, right? Like, if we kind of break this down to types of data fields, right? The more rich the data that we're going to have, the better any kind of twin model, any kind of modeling, any kind of analytics, any kind of future projection it's going to be, I would assume. And what? So you were talking earlier around capturing energy information and occupancy. Are there other types of data inputs that would benefit a twin model?
In a larger scale, yes, when we're looking at the context, for example, air pollution, air quality information, and when we are making some retrofit scenarios, when we're considering the context. For example, in another project that we recently did for Chicago, we are looking at spatial disparities of the exposure to energy, to air pollution, and how it influences energy efficiency strategies such as natural ventilation applications. So for such a scale that it can be a question of equity as well. So how different neighborhoods have that level of exposure differently across kind of a city. So it can be another facet that we can look at it as well.
Jeremy, if you don't mind me jumping in on that.
Yeah,
one,
no, go right ahead, Troy.
I actually don't think data or the number of sensors is really the relevant question. I think the big missing thing in smart systems, whether you're doing fault detection or doing control, is the missing ontology. You can make up for a lot of missed data and a lot of sensors if you have a ontology, and I mean ontology in the truest sense of the word, like this real representation of the building, not like the semantics of, say, tagging or categorization system. And that's the fundamental thing you need. And if you have that, you can fill in a lot down the line.
So I appreciate that. So we've got 2 minutes left, and I'd love to just maybe go through the panel real quick. Future state, we could solve one problem around or where we go with the next level of beyond fault detection, and we'll start with Joe and work through 30 seconds. What's the one thing you would change and do differently?
I would say they integrate multiple building energy system into a larger platform, not just the building automation system. So they integrate every energy system and then run the optimization at the top layer so that we can cover all the systems.
Okay, Jessica.
Think about scale and our goals. We've got, 6 million buildings that we need to get at. And I think that's really contingent upon being able to get at the work our way down the size spectrum to ever smaller buildings with tighter margins, with fewer staff. And if we can evolve our solutions to a place where they work not only for the most sophisticated, best resourced organizations and buildings into solutions that are more applicable, then I think we're going to reach that level of scale that we need.
All right, Troy.
Yeah, I think I obviously leaned out forward with our view of the future. So I'll take a little bit different slant of saying that we as an industry, that's federal, ASHRAE, in industry need to come up with standards for smart buildings, and we need to come up with standard test suites for levels of autonomy, so that we can talk we don't have to come to meetings like this and like put out in front where we land. We can dispense with that. We just say, I'm level 2, I'm level 3. And we know what we're talking about.
Okay, Narges.
I believe integration of or collaboration among multiple groups from researchers, stakeholders, building owners, and technology developers, as well as policymakers, can play a significant role how we can make a platform to bring all these agents together to make a big difference.
All right. Well, I want to thank all of the panelists who spent the time to come here and talk to everybody about, what's beyond fault detection. I'd like to thank the Smart Building Center for hosting the Smart Building Exchange, and hope everybody enjoys the rest of the session or sessions, the rest of the conference. Thank you very much. Have a great day. Thank you all.
Thank you.
Thank you.